Hello, my name is Michael. You're welcome to my YouTube channel. Today, I'll be talking on the topic IPv4 IPv6 Network Connectivity. This is a scenario-based lesson and I hope that you will enjoy it. The agenda today is as follows. We'll start with a scenario where I will share the background information as well as the briefing. And in this, we will find out the requirements, the constraints, as well as the goals. Then I will share with you the design and architecture of the infrastructure that has been prepared based on the scenario and the requirements. The implementation and verification part of it, I will show you, walk you through every part of it, and then we can reach a conclusion for this lesson. Please note that every information in terms of the IP addresses, whether V4 or V6, as well as the configuration, does not reflect any real company, entity, or systems. They are mainly fictional and they are for the purpose of education only. Thank you. And here's the briefing. So the summary of this scenario is a consulting company that won a contract from an enterprise to deploy IPv6 across different locations. This enterprise has 4 locations. 3 of these locations are lab centers where they are doing different kind of exploration as well as deployments within a small scale proof of concept and things like that, while they have just one main office. And all of these locations are interconnected using different WAN connectivity and technology. The locations are listed here, north, south, east, and then the main office. After this, we'll see what the documentation of the network looks like in terms of the designs, the architecture, the IP address, and other things that are necessary. So the architecture looks exactly like this, showing just the interconnection between the locations. And you can see here, we have the main office and the lab centers around the different regions that are existing. While here we have the IP address scheme for IPv4 and IPv6. As it has been stated before, some parts of the network already have IPv4, IPv6 existing. They just need this consulting firm to perfect their job in order to meet their requirement. And here we have the OSPF design. You would see also here that the OSPF scope is within these areas that has been identified. Any area where we don't have any OSPF scope, we don't run OSPF in such areas. Typical example would be here as well as here. So we stick to what we see on the design. The same thing with the BGP, which here we have 3 ASs as shown. The main office runs a particular AS, then the midpoint here, which is the core WAN aspect of the network, is also another AS, while the East Lab Center runs in a different AS entirely. And now we go to the task for the first point. Please take your time to read and we'll continue in a few seconds. Okay, so I believe that you understood the requirement, and if you don't, I will quickly summarize this. So this task wants the team to establish a particular connection between the main office and the East Lab environment. And how they want this to happen is such that a team of application developers, it's a small team as specified, they need to initiate the connection between their laptop or their endpoint device towards a specific gateway, which is running on IPv4 address as specified here. And we saw that IP in one of the documents that was revealed previously. We will take you back to it. What they want in addition to this is that the moment a success happens in terms of the establishment of that tunnel, a new adapter will be created on the developer's device, and that adapter will automatically acquire an IP address, which is an IPv6 address. Thereafter, that developer will be able to connect to one of the servers in that lab center. Now, when the IP address is being acquired, it will also have this string in some portions of that IP on the application developer's laptop. And that's all that we know. Now, very typical in design, you will get a lot of requirement in text form. Sometimes you have to deduce it from some information. Sometimes you are given by design. Sometimes you don't even have this information because the client has no details or knowledge, let's say the expertise of how to get to achieving the specific goal that they want. And when this happens, the best way to go about it is to translate the requirement, no matter how flawed it might be. You have to translate it into an implementable design, whether in Sketch or some other means, to reveal what might be hidden in all the information that you have. And this is typical even in the CCD exam, that is a Cisco Design Expert exam. That is very important skill, which is the requirement identification and analysis of certain requirements. And here we have a similar example where we are given this information. Now we have to translate this into the design. And here you can already see it asking us to go with the isotype tunnel. That is a constraint in itself, because it already tells you there is a preference of this particular client and this is the preferred option. That makes it a constraint, as well as the requirement of getting this goal achieved. So we will then see what we have. In terms of the design, here is what we are expected to do. Establish a tunnel between the laptop towards that gateway. And here is where I'm sitting. That's my laptop, which connects through my home network towards the lab. There is a converge point here to reach this. Let's go through it quickly. So we have to do a quick ping test. And that means I'm fine to reach there. We can also quickly run a trace route, which is 121.254. Okay, now that is fine. The next thing is for us to go to that router, that's the node, and then quickly check a few things. Since we already know it's going to be isotype, then we can quickly check if there is a tunnel. There is no tunnel yet. We have to establish the tunnel. We have to configure it. So these are the IP addresses, IPv4, IPv6 addresses on this router. And the next is to deploy the tunnel. Then we set the mode, which is IPv6 IP isotype, and we set the source to be that of the loopback, because that's the source that will receive the request from the endpoint of the application developers. Then the next after this is to configure the IPv6 address on this tunnel, and that IP we can do quickly, which is FC06 2026 22.192:164 AU I64. For details on how this IP address comes to determine 64-bit on this, you can check my previous video on this, on isotype topic. I covered that in detail in those videos, because there were two videos. One is separate and one is part of this series. So you can check both, and if you have any questions or doubts or some challenges, feel free to write me and I'll be glad to support you getting some clarification on it. Okay, now that we already have configured this interface, we can see that it already acquired that IP, and here we can see it's an isotype IP. So we go now to the PC, that is the application developer's PC, which is mine in this case, and we quickly check a few things. So first and foremost, we can check the list of adapters on this system to see if we have any isotype. we don't have any isotype. This is wireless, 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 and that's still scale and Ethernet and all that. So no isotype. The next thing we need to check is the isotype interface as well. So we check using this Windows command, and we do show router. We can see that the router name is the IP address of the gateway where the isotype will terminate, and in this case it's not the one provided, so we'll change that. The next thing to check also is the status, and here it is disabled. So we have to do two things. One, we set the router to the IP provided in the scenario. So we go quickly back. Last scenario, we're given this IP, so we can go to our prompt 192.254. As soon as you do that and you check, you see it's already changed and updated it. And the next will be to enable. But before I will do the enable, let's capture the moment on Wireshark and see how indeed this works. So I will filter to the address 10.22.192.254, so we can see exactly when it's initiated. The next thing is to initiate, and you can see what happens. It sends from my PC a solicitation message as the request to say I want to connect, and then it gets to send back an advertisement, and you see that coming from the router. As you can see, for details on this IP header, you can also check the previous video. And here, what I just want to point out is I'm using the unique local addresses, which, as you can see, not that one, the unique local address here. So those are the link local because it seems to be directly connected. That's where it sends this. The other part is the unique local address, which is unique local unicast address. And there it means we can now see the isotype adapter in the list. So this is wireless, and this is what we are looking for. The isotype adapter, which acquires an IP automatically. Remember, it's a tunneling protocol with automatic way of acquiring IP generally. And so we will be able to reach the tunnel IP if we decide to ping it from the PC now, which simply means we have established the connectivity to the router 5. But beyond that, you can also see from the design, this is the server. It's not directly connected to router 5, which means we need to ensure that there is a propagation of this subnet towards router 5 and backwards. As I said before, some parts have been done, so we just need to go and verify, and we'll see how that plays. So first and foremost, here there is a BGP running between the two systems, so I just do filter, and here we can see the advertisement here. So this is the advertisement of the subnet which belongs to the tunnel 192. So you can see that the subnet, and that is the subnet. The next we need to check is on the router 6 where the server is terminated, and we have to check what we have in there. So when we do, we can also check here, which is filter to network. We can also see that it's coming from router 5 through internal BGP, IBGP, and that's the subnet. In the same vein, it's advertising the subnet of the server, which simply makes it interesting. So now we should be able to test between the laptop and the server IP on this protocols, ICMP, SSH, and HTTPS. So we go back to our PC. Now we check. Okay, yes. I'm going to change this to A. and that tells us already that it's reachable. So we want to see what happens. So we can see the response here, the request, the response on ICMP looks good. We can now check that of the SSH, which is credential. See, the SSH session is running there as well. And you can see also the in. And if we check the IP addresses, we can also see here it shows we are on the right server. So that works. Next is to check the HTTPS. You can see also the session HTTPS is running, and that means we have successfully established the required session for task 1. So task 1 is done, and that's not all, because we have other tasks to complete. But very importantly, once you're done with this, it's all done. There is no need to extend it beyond this level, except if otherwise it's going to add value to the overall deployment. If not, it's going to become something called gold plating, which usually doesn't help. So we go to the next task, and I will give you some time to read through this as well. Okay, so I believe that you have read through, and if you don't understand how to go about this, I would explain it quickly. So the scenario here is also telling us the other part of the requirement which this client needs. And now it's on another lab center, which is the South Lab Center. In that lab center, they're running only IPv6. And the main office is running IPv4 only. But the client wants a connectivity between that main office and the South Lab Center, which doesn't make sense ordinarily, because IPv4 cannot automatically speak with IPv6 except through certain mechanism and means. And in that case, they have told us here that the servers in that environment only have this routing information of an IPv6 upstream device. That information is with this pool of IPv6 addresses. And the users, again, from the main office can only reach the South Lab Center through this IP address. And for us to test, we need to target this IPv4 in order to reach an IPv6 address of the server. What do we do in this case? Again, you have to analyze the requirement. You have to find out if there are any restrictions or constraints, and you have to target the goal. That's the essence of putting all of this information together and extracting what you need in order to proceed. And typically in this case, we have a constraint. The constraint here is we do not have a way of reaching the IPs that are original, and simply we will find a way of getting this done. But they have given us a little bit of some information here, which is the technical team of the consulting firm has been tasked to implement a solution to establish the connectivity between the locations, the main office and the South Lab Center networks, ensuring that the original source addresses are hidden from the servers. You can ignore this, that's a typo. So, which means what we have here is a form of translation, because translation simply hides one IP behind the other, and that's typical of what we want to do. But in this case, it's not a translation within the same version of IP. That is, you're not translating from one private IPv4 address to a public IPv4 address. No, we are translating from a private IPv4 address to another IPv6 address. So that's typical of what we are doing. And that means we would use the NAT option of translating IPv4 to IPv6. Again, we have to put this into an implementable design, which is here. So we have this IP address showing a connectivity between the gateway and the internal network. And we also have an IPv6 network here, which already shows us this only IPv6, and that's all that we have. We will then go into the router 1 is our target in this case. So we go to router 1, then we check a little bit of some parameters that have been configured. So we have this IPv4 parameters. We have IPv6 parameters as well. You can ignore the NVI previous deployment. So now let's check if we have anything with respect to NAT64. There is nothing. We can also check NAT64 translation table. There is nothing. So we will start from defining the NAT interfaces. First and foremost, these interfaces are this part and this part, and this will be Ethernet 00 and Ethernet 1, 2, 3. So we can check that on the device again. So we have this and this to be the NAT interfaces, and we can quickly put that through. Interface range 1, 2, 3. NAT64 enabled. So, okay, we have defined the NATs, and the next thing is, let's look back to the scenario. They gave us a pool of IP. So this is more or less a pool of NAT IPs, where certain IPs will be pulled from in order to hide the original IP of the main office behind this so that we can reach these servers. At the same time, we would have to target this IP in order to reach one of the servers of the South Lab Center, and that's exactly what we'll do. For this, we will go back to router 1, and I have a line of config which already can give us that configuration. So we have to define first the prefix for the NAT pool, and we'll have to define a static NAT as well. So that's basically what we have to do. While I wait for that, try to put this through. We just say prefix stateful, and then we copy that IP which is here. That's the pool that was provided, which the South Lab Center servers know about. And that simply means it will pick any IP from here to replace our internal IP. And the next line, which is here, is a static NAT, which is going to translate every packet that is destined to this IP into one IP pulled from here, which then is destined to this original IPv6 final destination. So it's more or less rewriting the destination IP from what it received to what it should go to. And that's exactly what we do here. And based on this, okay, just before we do this part, let's go now to this system to check if we are able to reach this IP. So this is supposed to be the IP of the server in the South Lab Center. At the moment, there is nothing like that exists. As soon as we enable this, this should then start responding. And by the way, we can also check the 64 translation table, which only has this but nothing more. At the moment we have it configured and we initiate this, you can see it's now reachable because there is a translation going on that table. And here we are going from original to original, that is original IPv4 to original IPv6. But what has happened here is it takes the original IP, translates it into this IPv6 IP, and because we are targeting this IPv4 address, which is also being translated to the original destination IPv6 address. That's exactly why it seems like a zigzag when you go this direction, or like an X. That's what we have. And simply we have established the connectivity between the main office and the South Lab Center. The next thing is to test again to the SSH. We'll quickly do that. And by the way, when we check in here, we have to change this to 202.0.6. You can see all the flows here, which is going directly. It's just directly to IPv4. But for us to see more, we can also see what is going on this side. So we will target this interface to see exactly what is coming out to this point. So when we initiate again, you can see it's ICMP. That's exactly our flow, and it means it's been translated correctly. That's one of the poles that we have. So, and this is more scalable than when you consider the tunnel, because you don't have to do anything on the client's end like we did in the case of the tunnel. It's just going to be on the NAT gateway itself. Okay, then with respect to the session here, we have to try SSH as well, and that's where we come in to do SSH, send credential, copy this IP, and then we log in. This is a different server, by the way, and now we are in, and when you check the IP address, you can see there is no IPv4 except for the loopback. Here we only have IPv6 Ultra, which is all good. And again, it means we have established the connectivity that is required, and that's our flow SSH wise. On this side you see IPv4, but on the other side you see the IPv6, which is here. You can see it's mainly coming from our origins. Okay, now task 2 has been done, and that means this design is fine. We go to task 3. For task 3, I'll leave it also for you to read so that we can wrap it up. Okay, so in this case, you would have realized that there is also a constraint that was provided. There is a requirement, there is a goal. The constraint is telling us here that it wants all servers to be able to reach one another without hiding their original source IP addresses, whether in the case of IPv4 or IPv6. At the same time, it wants them to establish connectivity together. That's the goal. And it wants this connectivity to be for IPv4 and IPv6, which is also the requirement here, is stating that there is need for these servers to be able to talk on IPv4 and IPv6 levels. Typically, this is nothing but a dual stack, which requires us to ensure that we establish the connectivity among the servers. And for this to happen, we need to translate this again into an implementable design. And to do that, we have it here. All segments that has the server and that interconnects them must have the IPv6, IPv4 connectivity options, which is the dual stack. And that's exactly what we have here. So we quickly go into each of the routers and then ensure that we have this connectivity. And mind you, we have the OSPF, so we have to ensure that OSPF is fully converged where it should be. We also have BGP where we should have it. Then we can do redistribution where there is need for us to redistribute. Then we will test across board. So that's for the OSPF. I will go to router 1 now to check if we have OSPF for both. So this is OSPF. We only have it converging with router 4. And for IPv6, we have it converging with both router 4 as well as router 2. So that looks good. We will just have to go to router 2 to enable the OSPF v2 here. So let's see. Okay, it doesn't have it because it doesn't have the configuration yet. So it does, by the way. Oh, okay, that's for IPv6, so we just need to replicate. Mind you, the OSPF version 2 and OSPF version 3 have the same topology, so we just follow whatever exists before now, and that's exactly what we do. 1, 2, 3, and 2026 and area 0. So with this we should be fine. Now we just yeah, that's already the case that we have established connection. Okay, and what about IPv6? Okay, so that looks good. Then we can also see here it already have the connection, but it appears that OSPF version 2 doesn't have connection yet. It doesn't have adjacency with route 3 yet, so we will go to that. Because the IP address we need here will be IP address 10.20.22.202. Exactly. 2.55255. That should be 24. Now we can enable OSPF area 32. We'll make it 100. There are only 2 of them there. We would then go to router 3 to do the same. So router 3 already established OSPF version 3 with 4 and 2. That's router 4 and router 2, which is good, but it appears not to have the version 2 of OSPF. That we will do. Again, we will quickly implement this 10.22.202.3 55255. Now specify the network and area 32 should converge also. So let's check it out. 10.22. Yeah, that's it. Okay. That's fine. The next thing we may want to do is to configure the HSRP, which we need to do. And there we can say 22 IP 10.22.202.1, and we can specify everything else 150, and we can also say preempt here, enable. Then we need to do same for router 3, standby 22 IP 10.22.20, and now we preempt. That is sufficient for time. What else? We just preempt and our name. It's all good. Alright, then we'll go here. Okay, so we now have them established the session with router 2 being the active router, which is fine. Normally we should do the tracking, but we don't have to in this case. So that we are only concerned about the outgoing traffic from the server, so that's not a problem. And we are not going to simulate the failure part of it, so that's fine. It's very important to do the tracking of the WAN interface of the primary router so that you can have a fully resilient network. Otherwise, you would have a situation where when there is a failure on the WAN, this entire segment would not know about that, and this would remain the primary for as long as this connection remains active. So it's very important to consider that tracking so that this would decrement its priority for the backup router to take over. That's typical of first up redundancy protocols. Okay, and now we have router 3 also ready. As you can see, it's standing by, which is all good for us. Now we go again to the next phase, which is router 4. Router 3, by the way, we have to talk to this router 6 because we need them to be ready. But let's configure the IP addresses. So we go to router 3. Router 3 is here. This will be fine, but we need to talk to 6, which is Ethernet 02. So to go to Ethernet 02, configure Ethernet 02 IP address. It's the IP 2236.1/29. 2236.3. The same thing address. Let's see, 36. Is it 36? Yeah, 36. 3, 125. Okay. Shut it. Remember, this doesn't run OSPF, so we leave it there. Now we move to router 6 to do the same. And this case is Ethernet 02. So come back here. Ethernet 02. Now quickly do that. 02. Address 1022.36.6. 524.524.8. And the same thing happens in this case. FC 06 2026 36 125. Okay. Now we just do a quick check, sure that we have everything. Okay, so that looks good so far. Then that is 2236.3 is ARP and then it responds. Okay. Alright, so we have this part also ready, and now we have to check this part to be sure that we are good indeed. So we check if we have everything intact with respect to router. Yes, it seems okay. And if we do a ping test quickly, and oh, perfect. So the same thing with the this should be yeah, okay, that's good. So this should be 4.4. Alright, so we are fine. Now the next phase is for us to check the BGP session. So OSPF all good, but BGP session isn't so good. And we can check first on the router 4. There's no router 4 here, so go to router 4, check we have on the OSPF. You can see this is coming from the south side, which is good, but we need to see what the BGP session looks like. So we need BGP to run among these routers. This already has BGP, so no problem, but here we need BGP to run. So we quickly go again for both versions 4 and version 6. So we go, if we have anything for BGP already, that already runs, but it's version 4, so we can add another layer to that. And we have to turn that on is address family, and we need to get the IP address, those parameters, and that's this one. So we have to do that of 2 and 4. So we are the same category IPv4, we have to make next up self. Okay, and that should be good up to this point. We move to the other ones quickly. Okay, so 26 and BGP. Okay, do this 1, 2, 3, 26, and we activate it for 6. Activate it, and the same thing with and the same thing for 6, version 6. Okay, so we have this already. Just need to check that the IP address of the version 4 is tagged. Okay, yeah. So okay, that's fine. The next is to check router 1. So I will go ahead to complete the rest of it so that we can verify, and then we will reach a conclusion of this. So I already have configured the routing protocols to be converged. Each of these routers have their peers in IPv4 and IPv6. We can see this also quickly. Each of the routers, so if we go to BGP, we have this, and if we go to the version 6 of the same BGP, we have this, and that is fine. Now what we need to do is to ensure that each of the segments that is attached to router 4, router 6, and router 2 and 3 advertised into the routing protocol. So we advertise them into BGP, and then we will do redistribution because this area doesn't run OSPF. And by the way, once we advertise them into BGP, all of this should be fine. But if we have advertised them, let's say redistributed, disconnected into OSPF, as we had it here, we then have to redistribute OSPF into BGP in order for these sites to get them. So there is no need, we just put them into BGP right away. So we'll start with router 6. So to see if we are learning anything at all yet. Okay, we have 30 routes, but nothing is coming from 3, so we can see that is directly connected, but it's recursive because it's learning it also from the other side. But it's minor stuff, we can actually filter that out later on. To check 10.172, which belongs to router 4. So this prefix, we need to look for it. Does it exist? 10 seems to be coming from here, which is router 5. It's advertising to router 6, which also means it's coming from here this way currently, which is good. Let's check router 3, see what it's learning. Okay, we are not learning so much yet from here, so we can advertise those and see how that plays. Now we also check on router 3. So router 3 is not learning so much by BGP. That's because there's no redistribution yet. Do that soon. And another thing is because we are getting it from an IBGP session which is between them, and we don't have route reflector or confederation. So that's actually the reason we are not getting much info from this side. Okay, what about IPv6? So IPv6 we're getting from east side, which is fine. Also getting the same from router 4, and here is also from the east side. Okay, so same. If we go to router 2, check. Okay, 2 is receiving a lot because it's directly connected to router 1. Router 3 is not receiving because it has no direct connection to router 1, and its connection to router 2 is an IPGP. It can send it. Its connection to router 4 is also an IPGP. It won't send it to router 3. So that's except we have a configuration of confederation or route reflectors. That's mainly why it is important to go in that direction. But it's not the focus of this lesson, so let's move on. And now I'll go ahead to advertise all the prefixes so that we can check again. So when all of the important nodes have been configured properly and correctly, you will be able to reach the servers across the locations. And as I said before, in an IPGP, when you have a partial mesh, that is, they're not directly connected, you would have to employ BGP confederation or the other option, which is BGP route reflector. And in this case, it's very important if we consider these as the reflector, so that router 4 and router 2 can be seen to be the reflector client, and that will help the connectivity or the propagation of prefixes from this segment towards this segment through that reflection. And that's exactly what I did, which is in this case, if you would check the configuration on this side, that is what we have, where we define the reflector clients for both of them, router 2 and router 4. The same thing can be applied to the IPv6 option, which is what I will do now as well. IPv6, just copy each of those and then define it to be reflector clients, and the same as that. Okay, now we can test the sessions. So we target this server and then we ping towards the other servers. So I have already configured the IP address here, which is IPv4 in this case, and I can now try to ping the IP address of the server, which is at the other location, that is the server here, which is .10. I can also run a trace route to be short. We are going through the router 2, so you can see it's going through the router 2, which is this way, goes through this path as the active, goes through this router, and then it gets to final location. So as soon as you have all the points configured and implemented, you would see that you are able to reach the servers across board. That is, from this server you're able to reach the other two servers, and let's check that out now. So on this server, which is with this IP address 202, which is also a dual stack, see it's the 202 side, then we will go ahead to ping the other ones. So that's just 10. Okay, and then you run a trace route directly to the 10. You can see it's going through this server and this router, which is router 2, goes to router 4, and then goes to the other server, .10. In the same vein, if we try to ping 192.0.254, which is the other server on the east side, that's this one, you can check again through trace route. 192.0.254, and this time around it's going through let's shrink this up a little bit, and now it's going through router 2 being the active. The router 2 sends it to router 3, router 3 then sends it to router 6, as we can see, and that's mainly how the connection traversed, or the packet traversed, which then eventually made it to the server. I hope this has been helpful to you, and I hope that you have time to reproduce this and try to play with this, make things happen. Now, that's actually our OSPF and BGP, and bringing everything together simply looks like this, where we have the tunnel directly from the application developer's PC directly to that router 5 as the gateway of our isotop. We also have the NAT, which is translating anyone coming from the internal network of the main towards the South Lab Center. And of course, we have the dual stack implementation, which allows our servers to be able to reach one another. What is important mostly is to understand the criteria, the requirement, the constraints, as well as the goal. And we could not have done this if we didn't have a converged network. And that comes from the core routing, which is including the OSPF, the BGP, the redistribution, where we have to do, because in this case, where we don't have OSPF running, we have to redistribute between BGP and OSPF, as well as on the router 4. And I believe also that you would have some time to play around a few of these concepts. Thank you for staying with me on this one, and I hope that you have learned one or two things. And for those of you who already know how to implement this, I hope you were able to get a refresher with this session. Until I come your way again, thank you for viewing. And please remember to like, share, and subscribe. See you next time. Bye.